Welcome to DAR Tutors. Today, we will explore the factors that shift the position of chemical equilibrium. The goal of this session is to understand Le Chatelier's principle and apply it to predict changes in equilibrium systems when conditions like concentration, pressure, and temperature are altered. This topic, known as Le Chatelier's principle, is a fundamental concept in chemical kinetics and thermodynamics, crucial for the IB Chemistry higher level curriculum. Let's begin by stating Le Chatelier's principle. It states, if a change of condition is applied to a system in dynamic equilibrium, the equilibrium will shift in a direction that tends to counteract the change. This means that a system at equilibrium will attempt to oppose any disturbance you introduce. It's a key tool for predicting the response of an equilibrium system to changes in concentration, pressure, and temperature. A critical point, which is a common misconception, is that Le Chatelier's principle only applies to systems that have already reached equilibrium. You cannot apply this principle to a reaction in its initial state or while it is in the process of reaching equilibrium. The system must first be in a dynamic equilibrium where the rates of the forward and reverse reactions are equal. The first factor we will examine is changing the concentration of a reactant or product. Let's consider a generic reversible reaction. Suppose we have reactant A and reactant B in equilibrium with product C. Now let's say we increase the concentration of reactant A. This change disturbs the equilibrium. According to Le Chatelier's principle, the system will shift to counteract this change. To reduce the increased concentration of A, the equilibrium will shift towards the right, favoring the forward reaction to produce more C. In simpler terms, adding a reactant shifts the equilibrium away from the side where the addition was made. Conversely, if we remove some product C from the mixture, the concentration of C decreases. The system will then shift to the right to produce more C and replenish what was removed, counteracting the change. So removing a product also shifts the equilibrium to the right. The system always tries to restore the balance by moving in the direction that offsets your action. Let's apply this to a specific chemical example from your notes: the synthesis of ethyl ethanoate. The reaction is ethanoic acid plus ethanol in equilibrium with ethyl ethanoate and water. This is an esterification. The question asks for the effect of adding a small amount of concentrated sulfuric acid, a strong dehydrating agent, to this system. First, we must identify the role of the sulfuric acid. It acts as a dehydrating agent, which means it will react with and remove water, H2O, from the equilibrium. Removing water is equivalent to removing a product. According to Le Chatelier's principle, the system will counteract this removal by shifting the equilibrium to the right to produce more water. This shift to the right, towards the products, means more ethyl ethanoate is formed. Additionally, sulfuric acid is a strong acid that provides H+ ions. These ions act as a catalyst for the esterification reaction. However, remember, a catalyst speeds up the forward and reverse reactions equally and therefore does not affect the position of equilibrium. It only helps the system reach the new equilibrium state faster. The primary effect on the equilibrium position comes from the removal of water, which drives the reaction to the right, favoring ester formation. Now, let's address another crucial point: the equilibrium constant, K. A common misconception is that adding products to an equilibrium system increases the value of K. This is incorrect. When more products are added, the concentrations of all reactants and products will change in such a way that the value of the equilibrium constant, K, remains precisely the same. The only factor that can change the value of the equilibrium constant, K, for a given reaction is temperature. All other changes, concentration, pressure, or adding a catalyst, do not affect the numerical value of K. They only affect the concentrations of the species at the new equilibrium position. This is a fundamental concept that IB examiners often test. Always remember that for a reaction at a constant temperature, K is a constant value that reflects the ratio of products to reactants at equilibrium. Next, let's explore the effect of changing pressure on an equilibrium system. It's important to remember that this factor is only relevant when the reaction involves gases. If we increase the pressure, Le Chatelier's principle tells us the system will shift to reduce the pressure. The way it does this is by moving in the direction that produces fewer gas molecules. The fewer gas molecules you have in a container, the lower the pressure will be at a given temperature. So, to counteract an increase in pressure, the equilibrium shifts to the side with fewer moles of gas. To counteract a decrease in pressure, the equilibrium shifts to the side with more moles of gas. A critical exception is when the number of moles of gas is the same on both sides of the equation. In this case, changing the pressure has no effect on the position of equilibrium, because shifting in either direction would not change the total number of gas moles. Let's look at an example. The notes discuss the Haber-Bosch process for synthesizing ammonia. The equation is 1 mole of nitrogen gas plus 3 moles of hydrogen gas in equilibrium with 2 moles of ammonia gas. First, let's count the total moles of gas on each side. On the reactant side, we have 1 mole of N2 plus 3 moles of H2, totaling 4 moles of gas. On the product side, we have 2 moles of NH3. So, the right side has fewer gas moles. The question is, what is the effect of an increase in pressure? An increase in pressure will cause the equilibrium to shift to the side with fewer gas moles to reduce the pressure. In this case, that's the right side, the product side. Therefore, an increase in pressure will favor the production of ammonia, shifting the equilibrium to the right. This is why the Haber process is conducted at very high pressures. It maximizes the yield of the desired product, ammonia. Now, let's explore the effect of temperature on the position of equilibrium. This is a bit more complex, as the direction of the shift depends on whether the forward reaction is endothermic or exothermic. It's also crucial to remember that temperature is the only factor that changes the equilibrium constant, K. According to Le Châtelier's principle, if we increase the temperature, the system will try to cool itself down. It does this by favoring the endothermic direction, which is the direction that absorbs heat. Conversely, if we decrease the temperature, the system will try to warm itself up, favoring the exothermic direction, which is the direction that releases heat. Let's summarize. For an endothermic forward reaction, an increase in temperature shifts the equilibrium to the right, and the value of K increases because more product is formed. For an exothermic forward reaction, an increase in temperature shifts the equilibrium to the left, and K decreases because more reactant is formed. This table is an essential tool for predicting temperature effects. It's vital to know the sign of the enthalpy change, dH, to determine the nature of the forward reaction. Let's apply this to the equilibrium between dinitrogen tetroxide and nitrogen dioxide, which you saw in the notes. The equation is N2O4 in equilibrium with 2NO2, and the enthalpy change, dH, is positive 57 kilojoules per mole. A positive dH value indicates that the forward reaction, the decomposition of colorless N2O4 to brown NO2, is an endothermic process. The forward reaction is endothermic, so absorbing heat from the surroundings. The reverse reaction, the formation of N2O4 from NO2, is therefore exothermic, releasing heat. Now, let's predict the effect of increasing the temperature. An increase in temperature will favor the endothermic direction, which is the forward reaction. The equilibrium will shift to the right to produce more brown NO2. This means the gas mixture will become darker in color. Conversely, a decrease in temperature will favor the exothermic direction, which is the reverse reaction. The equilibrium will shift to the left, producing more colorless N2O4, and the gas mixture will become lighter. This is a classic demonstration in chemistry, where you can observe the color change by placing the mixture in a hot water bath and then an ice bath, as shown in figure R289 in your notes. We have seen how concentration, pressure, and temperature affect equilibrium position. Now, let's consider 2 factors that do not affect it. First, a catalyst. A catalyst works by lowering the activation energy for a reaction. However, a catalyst lowers the activation energy for both the forward and the reverse reactions by the exact same amount. As a result, a catalyst speeds up the forward and reverse reactions equally. This means it helps the system reach equilibrium faster, but has no effect on the final equilibrium concentrations of reactants and products, and therefore no effect on the equilibrium constant K. The position of equilibrium is unchanged. Second, the surface area of a solid. For heterogeneous reactions involving solids and gases or liquids, a larger surface area will increase the rate of reaction. This is because more particles are exposed for reaction. However, this increase in surface area increases the rate of the forward reaction and the rate of the reverse reaction equally. For instance, in the evaporation of a liquid, increasing the surface area allows more molecules to evaporate, but also more molecules to condense. The rates increase proportionally, so the equilibrium position remains unchanged. Here at DAR Tutors, we offer expert tuition in IB A-level and IGCSE curricula. Whether you need help with the fundamental concepts of chemical equilibrium or want to master the advanced problem-solving techniques for higher-level exams, we have the resources and experienced educators to help you achieve your academic goals. We provide personalized online and home tuition tailored to your specific learning style and needs. Our goal is to make complex subjects clear, foster deep understanding, and build your confidence. So if you or your child could benefit from expert guidance, we encourage you to contact us. Visit our website at dartutors.com to learn more about our programs and how we can support your journey to academic success. Now, let's work through some additional examples to solidify your understanding of these principles. Example 1. Consider the synthesis of methanol. The reaction is carbon monoxide and hydrogen in equilibrium with methanol. We are given the enthalpy change, which is negative 128 kilojoules per mole. First, let's analyze the effects of pressure. On the reactant side, we have 1 mole of CO plus 2 moles of H2, for a total of 3 moles of gas. On the product side, we have 1 mole of CH3OH. The product side has fewer gas moles. Therefore, increasing the pressure will shift the equilibrium to the right, increasing the yield of methanol. Next, temperature. The enthalpy change, DH, is negative 128, meaning the forward reaction is exothermic. An increase in temperature would cause the equilibrium to shift to the left, decreasing the yield. Conversely, a decrease in temperature would shift the equilibrium to the right, increasing the yield. Let's look at another example involving an aqueous equilibrium. Example 2 involves the equilibrium between chromate and dichromate ions in water. Chromate, CrO42, is yellow, and dichromate, Cr2O72, is orange. The forward reaction has a positive enthalpy change, meaning it's endothermic. Predict and explain the color change if you add a strong acid like HCl. When you add a strong acid, you increase the concentration of hydrogen ions, H+, a reactant. To counteract this increase, the equilibrium will shift to the right, towards the products. Since Cr2O72 is orange, the solution will change from yellow to orange. What if you then add a strong base, like NaOH, to the orange solution? Adding a strong base will neutralize the H+ ions, effectively removing them from the equilibrium mixture. To counteract this decrease in H+, the equilibrium will shift to the left, favoring the reverse reaction. This will produce more yellow CrO42, and the solution will change back from orange to yellow. This is a reversible color change often used in laboratories to demonstrate Le Châtelier's principle. We've now reviewed the core principles and worked through several examples. It's time to test your understanding with some IB-style practice questions. Take your time to answer each question before I reveal the solution. Pause the video if you need more time. Question 1 asks how adding a catalyst affects the equilibrium of the Haber process. Think about what a catalyst does. Solution. A catalyst lowers the activation energy for both the forward and reverse reactions by the same amount. It therefore increases the rates of both reactions equally, allowing the system to reach equilibrium faster. However, it does not change the position of equilibrium or the value of K. The final concentrations of N2, H2, and NH3 at equilibrium will be the same as without the catalyst. Question 2 gives us the equilibrium between sulfur dioxide, oxygen, and sulfur trioxide with a negative DH. We need to predict the effect of increasing temperature. Solution. The forward reaction has a negative enthalpy change, so it is exothermic. An increase in temperature will shift the equilibrium in the endothermic direction, which is the reverse reaction. The equilibrium will shift to the left, favoring the formation of reactants. Because the equilibrium shifts away from the products, the value of the equilibrium constant K will decrease. Question 3 involves the decomposition of calcium carbonate, which is an endothermic process. Solution. Pressure changes only affect gases. In this equilibrium, only carbon dioxide, CO2, is a gas. Therefore, we compare the moles of gas on the reactant and product sides. The reactant side has 0 moles of gas, and the product side has 1 mole of gas. An increase in pressure will shift the equilibrium to the side with fewer gas moles. This is the reactant side. Therefore, the equilibrium will shift to the left, favoring the decomposition of calcium carbonate. Question 4 asks us to consider the solubility of gases in liquids. Solution. The dissolution of a gas in a liquid is an exothermic process. That is, pH is negative. Heat is released when the gas dissolves. Increasing the temperature applies a stress to the system. According to Le Châtelier's principle, the system will shift to counteract this stress. It will move in the endothermic direction, which is the reverse of dissolution. The gas coming out of solution. Therefore, the solubility of the gas decreases with increasing temperature. Question 5 provides a reaction and asks us to determine the conditions that would maximize the yield of product B. Solution. To maximize the yield of C, we need to shift the equilibrium as far to the right as possible. First, let's consider pressure. On the reactant side, we have 1 mole of A plus 1 mole of B, totaling 2 moles of gas. On the product side, we have 2 moles of C. The number of moles of gas is the same on both sides. Therefore, changing the pressure will have no effect on the yield of C. Next, temperature. The enthalpy change, dH, is negative 150 kilojoules per mole, meaning the forward reaction is exothermic. To maximize the yield of C, we need to favor the forward exothermic reaction. This is achieved by decreasing the temperature. Therefore, the conditions to maximize the yield of C are a low temperature and any pressure. We have now reached the end of our session. Let's briefly recap what we've learned. We also learned that catalysts and surface area increase reaction rates but do not affect the equilibrium position or the value of K. Remember that K is a constant at a given temperature. I hope this detailed explanation and the worked examples have clarified how to predict the effects of changing conditions on chemical equilibria. This knowledge is essential for your success in IB Chemistry HL. Thank you for your attention. Thank you for watching this DAR Tutors video. If you found this explanation helpful and wish to receive further expert assistance in IB, A-Level, or IGCSE curricula, please do not hesitate to contact us. At DAR Tutors, we are committed to providing high-quality, personalized tuition that helps students master challenging concepts and achieve their full academic potential. Our experienced tutors are dedicated to making learning clear, engaging, and effective. Visit our website, dartutors.com, to discover more about our online and home tuition services. We look forward to helping you succeed.